Today we're going to show you another way to solve the systems of linear equations. First we showed you how to use the graphing method, where you would graph the two equations on the same coordinate plane and look for their intersection points. Then we looked at how to use the substitution method, which is a more algebraic way. Thirdly, we're going to show you the elimination method, which is another more algebraic way. So, as you can see here on the screen, it's a little bit crowded here trying to get all this in. I knew I could probably type it in a little bit easier and quicker and get it more words here. The steps we'll talk about real quickly, and then I'm going to just go through the few examples so you can see them actually played out. The numbers that you see on your paper, 1, 2, 3, and 4, we're going to kind of change those as we go through these. So just kind of follow along with the steps, and then we'll go down a little bit further and show you how they actually play out. So for step 1, and step 1 is right up on top here. What we're going to do is we're going to line up the terms in the like terms into columns. So what's going to happen in the elimination method is you're going to take the two equations and set them up so they are vertically. So like for example right down here, notice how they are set up on top of each other, and the like terms are lined up in columns. So step 2. Step 2 here, which is the next two lines, says to multiply one or both of the equations by some constant. Remember, a constant means a regular number, so that one pair of the like terms are opposite coefficients. Now, we don't have to always do opposite coefficients, but what I'm going to do is I'm going to show you today how to do this through adding the two equations. You will see that when you get to the high school that you can also subtract them, but just to try to eliminate a little bit of the confusion so that we don't get some problems with some of this, and to keep us all doing the same thing, I'm going to have you do opposite coefficients so that we just focus on the adding of the two equations. The third step, so this is now step 3, not the 2 that it looks like. Add the equations. That's going to eliminate one of the variables. So in the example down below that I kind of put the arrows on, you see x's and y's. And if we add the equations, our job is to get rid of either the x's or the y's. That's what happens in that step 3. And again, it doesn't have to be adding. We are going to use adding this year. You will hear next year at the high school that there is subtraction as well, and there's certainly nothing wrong with that. I'm just trying to give you the first step so that when you see this again, you can then look at the subtraction part. Step 4. So step 4 says to solve the resulting equation for the variable that's left. So basically what's going to happen is, as you add those two equations together, one of the variables disappears, leaving you with the other variable. So step 4 basically means to just finish the equation. You'll then have one variable and you finish solving that equation. Step 5, you're going to take the answer that you get in step 4, substitute that value back into one of the original equations to find the other variable. So we eliminated one of them to help find the first one. But then when we go back to the original equation, we now have a number for the first variable. We're going to have a variable still because we're back to the original equations where there were two variables, and then we're going to solve from there. And then step 6, we keep mentioning this, and it's an extremely important thing. Step 6 is to check your solutions. Again, there's nothing worse than getting an answer, thinking you have the right answer, and then kind of just moving on and it doesn't check. Remember, my solution has to work in both equations. So let's see how this works. So here we are solving by elimination. So if you'll notice in the very first part of this, we already have our two equations lined up in like terms. The x's are on top of the x's, the y's are on top of the y's, the equals is on top of the equals, and notice that's there. And then the other side, the constant, is on top of the constant. So for step 1, we don't have to do that. Step 2 says to multiply one or both equations by some constant so that we have opposite coefficients. Well, right here, we have opposite coefficients. Remember, the coefficient is the number in front of the variable. So we have a 3 and we have a negative 3. So really, step 2 is already done for us here. So now all I have to do is add these two equations together. So we draw the line underneath, we do a big plus on the outside, and I just simply add down. So x plus x is 2x. 3y plus a negative 3y cancels. The equals can come down, and negative 2 and 16 is 14. So that is step 3. Step 4 says to solve the resulting equation for the variable. Well, we have x's left over, so I'm going to undo the times 2 by dividing by 2, and I get x equals 7. So that's part of our equation, our solution. We obviously need the y value that goes with that. So next what I'm going to do is bring the x over here. We'll go back into the first equation just to make sure that we have one of the equations solved for. I plug the x in with a 7, since that's what we just determined from the first part. And now I just solve for y's. So I'm going to subtract 7 through SADMAP first, get 3y equals negative 9. Then I can divide by the 3, which means y equals negative 3. So that will tell us that the solution to this is 7, negative 3. I'm not going to show the check. You can certainly do the check to make sure that you can verify 7 at negative 3. The other part of this is keep yourselves neat so that you can see your two answers, and then when you come back to put it together, the x obviously goes first, followed by the negative 3. So our solution is 7, negative 3. On the second one, so now we look at one and we have, again, our columns are lined up, so that's good. We don't really have to rearrange anything, so I don't have to do that part. But what I do want to notice here is looking at my x's, I have a negative 6 and negative 2, and I have a 5 and a negative 4 for the y's. I don't have opposite coefficients at the moment. So what I want to do here is I want to multiply one of these equations by something that's going to get me opposite coefficients. Well, I believe that the first one that jumps out at me is this negative 2, trying to match the negative 6. So remember, I want opposite coefficients. So if the negative 6 is the coefficient in the first term, what I want is a positive 6 in the second term. So what I'm going to do is multiply this entire equation on the second one by negative 3. So when I do that, I want you to notice over here, the first equation is going to stay the same. So we have negative 6x plus 5y equals 25. In my second equation, using the distributive property and multiplying all the terms, including over the equal sign, is going to give me 6x plus 12y equals negative 42. So again, notice that that is my distributive property. There's the 6x, there's the 12y, and then all the way across, there's your negative 42. You have to multiply everything all the way across. So now I have my opposite coefficients. So then I can just add them together. The negative 6x and the positive 6x cancels. I get 17y, and I get negative 17 on the right. So to finish this equation, I just divide by 17. Y's equal negative 1. So then I'm going to take this equation, this value of that equation, back over to the other side. We'll go again just back through the first one. This time we have the y value, not the x value. So I'm going to plug in the negative 1 where I saw the y's. And now I'm just solving for x. So negative 6x minus 5 equals 25. I would add 5's to both sides. Negative 6x. Divide by the negative 6. X equals negative 5. So again, you should show the check. I'm not going to show the check on this one just for time and for space here. You should show the check, but our solution becomes negative 5, comma, negative 1. So here we have a real-life application. We're talking about the hostas and daylilies that my friend buys and that myself buys. Daylilies and hostas are flowers. So basically what we're going to do is set up two equations to help figure out the cost. What we're looking for as you read through this equation is we're looking for the cost of the daylilies, so we don't really need to know both. So for the first equation, I'm going to set up for me. So in this first sentence up top here, we talk about 8 daylilies. We don't know the cost, but we are doing the cost as the x. 8 hostas, 15 daylilies. The daylilies cost is the y, and the total of my bill was 193. My friend came in and bought 3 of the hostas, 12 daylilies, and spent 117. So there's my two equations. So by having my system, we have done the first part here, it says write the system. Next I want to look at my two coefficients that we're trying to deal with. So here we have 8s and 3s, 15s and 12s. Neither of those are opposite coefficients. I think though what I'm going to focus on is 24 to help me eliminate the x's. So if I focus on 24, I'm going to make my first equation turn into 24x plus 45y equals 579. And again, that is using my distributive property to make sure I multiply everything by the 3 on the outside. Okay? Then I move on to the second equation and I do the same thing. I'm multiplying everything. But in this case, now I want to get a negative 24. So I'm going to multiply the 3 by negative 8. So negative 24x minus 96y's. I just noticed here we forgot that little y there. And then what that is going to equal on the other side is negative 936. So now I have my like terms lined up. I have opposite coefficients on one variable, so I can add. When I add those 24 and the negative 24, they go away. Then I get negative 51y's, and I get negative 357. I can finish this equation now because I only have y's to solve for. Y's equal 7. So then what I want to do is move on to figure out what the x's that go with those y's are. You might say, well, I only needed to know y's because that's the daylily cost, and that is true. However, I think it's worth us going through and finding out the y's because of the check. If we somehow made a mistake someplace and it really shouldn't have been 7, and we come up with a value for the x that doesn't work, then that would tell us that we needed to do something else, and we can go back and figure out what went wrong. But yes, we are looking for the y value only. I think the check is still worth it. So notice here I'm using my SADMAP steps to get x by itself. 3x equals 33. When I divide by 3, x equals 11. So again, when I do my check, this will work out. So 11 of the hostas and 7 of the daylilies. So we can basically say $7 per daylily. If we needed to know the hosta cost, we also already have that, so that's a good thing. But each of the daylilies are going to cost $7. Each of the hostas would cost $11, although we don't really need to answer that for this question. So the elimination method is a great method to be able to use. Once you have practiced it more, it'll definitely be one that you will like. We want you to try all 3 methods at this point. Some graphing, some substitution, some elimination. Certain situations are going to dictate which is best for certain problems. And as you get better at all 3 of them, it'll be great to have your toolbox have an extra way of solving systems of linear equations.